Okay. Welcome back. So, yesterday we derived this equation. Called the Langevin equation. So, let me remind you what are the ingredients of this equation, which is a fundamental equation for stochastic processes, and how we arrived to that, and what are the physical ingredients of the method. Well, first of all, let's comment it. It's a Newton's equation with additional terms. This term accounts for the friction, the possibility that a system loses energy by interacting with the surrounding environment. Gamma, also known as the friction coefficient, has the unit of a frequency, and is also called the collision frequency for this reason. And it's basically the rate at which you lose energy by interacting with the environment. Psi is a stochastic force. And yesterday we showed that under conditions that we are going to review today, this force can be assumed to obey the following important properties. Having zero average, otherwise the system would drift towards the direction of the average, obviously. And having a time correlation that on average is given by following fluctuation dissipation relationship. This was the result we achieved yesterday. So let me spend a couple of minutes reminding you how we got there. And basically what I'm going to give you now is what I need you to really retain. You can think about yesterday's lecture, which was admittedly more technically involved than the others, as a bonus track, which you might learn for honor grades, or just try to capture the essence of it. And the essence of it is the following. We described the interaction of a system with an environment. Because that's exactly the situation we are when we want to study macromolecules, which actually live in a solvent, typically. We're talking about biological macromolecules in this course specifically. They live in water with ions, which does provide a heat bath. So the essential question is, how does the interaction with a heat bath affect the dynamics? To address this question, we started off with the only theoretical formalism we knew we could use at this level, which is the Hamilton's equation. But of course, we had to face the problem of dealing with interaction with the heat bath molecules, which is extremely complicated. So instead, we adopted a simplified description in which all the heat bath molecules were replaced by harmonic oscillators. You might think this completely destroys the dynamics, because there is no harmonic oscillator in a macromolecule in solution. However, throughout a detailed discussion, we came to realize that at the end of the day, once we arrive at this equation, there's no specific reference to any particular interaction type with the underlying heat bath molecule. We can physically interpret this as a friction, and this is a random cake taken from the environment. Right? So, in hindsight, in retrospect, in hindsight, the role of the harmonic oscillator was actually not that of describing actual physically grounded harmonic oscillator springs, but was that to me to introduce a mathematically treatable way of accounting for releasing information to a third party or to some degrees of freedom that are not mnemonic, and receiving that interaction back at a later time. Once we were able to do that mathematically, because harmonic oscillators have nice mathematical properties, we were able to see physics through it and understand that whenever the number of degrees of freedom in the heat bath become virtually infinite, and their dynamics much faster than the dynamics of the system, the actual physical origin of those degrees of freedom didn't matter anymore. What really mattered was the fact that you could exchange energy with those systems. And in fact, the friction here comes from assuming a continuous spectral density of the response function. Remember the propagator of the energy in this collection of harmonic oscillator, the kernel K. In frequency space, the kernel K had a set of spikes, but if the number of a harmonic oscillator becomes infinite, you would sort of distribute those spikes, and then you would say, okay, now I'm interested in the slow dynamics, I do a Taylor expansion of the spectral representation, which would give me a delta function time-dependent representation, and that's how ultimately you obtain just a friction coefficient here. So what you need to know is that the friction coefficient only makes sense if the dynamics of the, say, heat bath degrees of freedom is fast compared to the dynamics of the system. But as we already have mentioned at the beginning of the course, anytime there is a gap in dynamics, the details of a fast dynamics don't matter. And that's why we only get a constant here. Just as much as you get a multiple charge in the multiple expansion and dipole, regardless of the specific details of a charge distribution that generates the charge and dipole and quadrupole moments. Okay? So, this is to say that this equation is far more general than the way we derive it. In fact, there is a way that allows you to arrive to this equation that is far more general, that doesn't involve any particular harmonic oscillator models, and it's called the Mori-Fanzig projection formalism. I did not use that because it's a bit of a formal object. It uses projection operators in the Wheel space. It's very elegant, but I figured that the explicit construction we used, although a little bit long and tricky in some point, was more physically transparent because it enabled you to see in a very specific example how things work. Where does this energy balance come from? Okay? The second important point that I'd like to state is about the delta correlation noise. The delta correlation noise and the fluctuation dissipation relationship, meaning the specific value of this coefficient that enters here, followed from observing that the value of the stochastic force at time t only depended on the initial condition of the heat bath degrees of freedom, given the initial condition of the system. Remember, and since we didn't know that initial condition, if you assume the Boltzmann initial condition, so the system is initially at equilibrium, then you can obtain the average time correlation from a Boltzmann average over the initial conditions. And that's how this result was formally obtained. We did not really do the average, to be honest. But this is why this equation mixes together equilibrium and dynamics. It mixes equilibrium because the initial condition is at thermal equilibrium. Hence, the system knows what the temperature is. But it also contains dynamical constants because it needs to know the rate at which you exchange energy with the system from the initial condition to the given time. And like we emphasized yesterday at the end of the lecture, this is one of the few occasions in statistical physics where you actually see time and temperature on the same equation. Well, there is, of course, work in that direction. But this is not statistical mechanics 101, so to say, where you normally deal with equilibrium ensembles. Okay? So in other words, now we really are going past basic thermodynamics where your system is assumed to be always in equilibrium. Any change you do is by moving from equilibrium to equilibrium to equilibrium. Here we are saying, well, all that I'm assuming is that my environment is in equilibrium, so that I don't have an out of equilibrium heat bath. The heat bath must be at equilibrium at some temperature. Now, if you do that, we're now going to see that this relationship ensures that no matter what the initial condition of the system, which is embedded in the heat bath, is, the distribution of probability generated by this equation ultimately converges to the Boltzmann distribution. So, in other words, fluctuation-dissipation relationship ensures that you exchange right amount of energy to ultimately fulfill the zeroth principle of thermodynamics, thermalization. Okay? The delta structure of this correlation comes from the fact that we have assumed that the response time of the environment is very fast, so that the system loses memory of the environment configuration is almost instantaneously. In our little model, this was made explicit by the fact that a force was giving rapid fluctuations in time because it contained a series of, a Fourier series basically, sines and cosines with very large frequencies, which means that at any seemingly infinitesimal time delta t for the system, for any interval that is small for the system, because the system is slow, is actually a large interval for the heat bath, because they have different scales. So the heat bath reconfigures itself many times in any instantaneous interval. So many times that basically makes sense to assume that by any finite interval for the scale of the macromolecular system, the heat bath has lost memory. There's no time correlation. Okay? Now, You can think about the Langevin equation in phase space, of course. Right? However, now clearly this set of equations will take a point in phase space and evolve it. However, unlike Liouville's evolution, this is not deterministic. Remember, in Liouvillean evolution, I'm going to represent Liouvillean evolution as a dashed line now, and Langevin evolution as a continuous line. In Liouvillean or Hamiltonian dynamics, sorry, not Liouvillean, I meant Hamiltonian. In Hamiltonian dynamics, for every point in phase space, there is one and one trajectory only, meaning that if you decide that you are interested in the trajectory that visits at time t naught, this point in phase space, then you're going to get one trajectory, one orbit. Oh, I just promised I was using the dashed line and I didn't. So let me make this a dashed line. So this dashed line here is the Liouville, the Hamiltonian trajectory that goes through the point that I marked here at time t naught. And it specifies one trajectory in phase space. Well, because of the stochastic force, the Langevin dynamics works very differently. If I repeat the same simulations n times, the realization of the stochastic force is different every time, right? So, if I repeat the dynamics n times, I will end up, after the same in-time interval, into n different positions. And the reason for this lack of determinism is because in Langevin dynamics, this is in fact a projection. What do I mean? That we are representing the phase space of the system, but in Langevin dynamics comes from a Hamiltonian dynamics in a large phase space where also the environment's degrees of freedom are. Right? Now, the fact that I say different trajectories here comes from the fact that what I take as a point is in fact different points in the direction of the environment configurations that here I represent as a dimension coming out of the board. So if I start with different environment configurations, right, I will get different trajectories in phase space, but one and only from each. But when I project them onto the system phase space, I lose all of the information on where I started off, and I see the shadows of those trajectories on the system phase space, subspace. And the shadows of these higher dimensional trajectories in phase space onto the configuration of phase space of the system alone, the molecule, are this continuous line, and I have different shadows. But if I were able to disentangle them from here, looking in the third direction, I will see that these different lines would correspond to different initial configuration of the system, of the heat bath. Okay? So this is how a deterministic dynamics becomes stochastic in phase space if I integrate out the dynamics of the system, of the heat bath. Okay? Now, in the previous lectures, we spent a good time trying to figure out an answer to the following question. Given a distribution of initial condition, what is the probability density in phase space at any later time, right? And we discovered that this evolution of the phase space density, rho of gamma and t, was determined by the Liouville's equations. Which was particularly simple for Hamiltonian dynamics, Poisson bracket formulations. Now we might ask the very same question. If I start from an initial phase space distribution, or even an initial phase space point now, because what is the probability to end up in a particular phase space point t at time at a later time? So normally in the literature, this probability, which is the same probability as this, as a matter of fact, in terms of interpretations of density in phase space, but normally goes out, is denoted with P for stochastic process. So I will use the notation P. And for stochastic processes determined by the Langevin equation that I wrote in the upper part of the board, the equation that governs the evolution of the probability density in phase space is not the Liouville's equation, obviously. It's called the Fokker-Planck equation. Okay, so obviously a very relevant question is, can we derive that equation? And remember, since part of the reason we are taking this pain to go through stochastic dynamics is to use mathematical methods that are naturally embedded in the stochastic dynamics formulation, it is important to possess as many mathematical tools as possible, including the equation that governs the time evolution of the phase space density. However, since we have a lot of material to cover, I decided to make a compromise. I will discuss this equation in a particular limit, which is the one that is most relevant for practical applications. But before we go into that, let me just say that we can easily solve that equation by slightly perturbing the leapfrog algorithm we have already used. How? Well, adding a friction is straightforward because the leapfrog algorithm contains momentum and position, and the friction is given in terms of momentum. So all you have to do is to add a negative coefficient times momentum in whenever you integrate the momentum, right? But the most interesting part is, of course, the stochastic force. So anytime you're in the leapfrog algorithm, and wherever you evaluate that force, you have to add a stochastic force. And how do you add the stochastic force? You sample it from a Gaussian with zero average and variance given by this. We will become practical in a moment, in a specific limit. So basically what you're doing, you're writing a leapfrog algorithm with some friction, no big deal, in which you add a Gaussian variable every step over the way. And the variance of the Gaussian variable is set judiciously, precisely to be consistent with the fluctuation dissipation theorem, which in turn guarantees that your dynamics will ultimately converge to the Boltzmann distribution. That is, the static distribution solution of the Fokker-Planck equation will be the Boltzmann distribution. Correct? Does it make sense to you? deriving directly the Fokker-Planck equation, for sake of economy of time, and since we have a lot of material, we will introduce a further simplification, which is most often adopted by anyone who really tries to use the Fokker-Planck dynamics to interpret the results of simulations and to develop enhanced sampling algorithms. That is the overdamped limit. So, pronto, sono a lezione. Scusate, sono a lezione e cosa c'è questa? È partita una chiamata? Sorry. Okay, so let's work out the overdamped limit. Let's work out the overdamped limit. Do you remember the parachuter problem you did in first year? Meaning you have a system obeying Newton's equation with some friction. Remember that? And what happened to the parachuter problem? Well, if you look at the velocity as a function of time, assuming, for instance, you start from zero velocity, right? Instead of growing linearly, because the acceleration is constant, he would reach a steady state velocity, which for parachuters is of the order of 20 to 30 kilometers per hour, and that's why they don't die. So intuitively, it is clear that in the presence of friction, acceleration only matters for a transient time. Okay? Now imagine the following. Imagine that your elementary time resolution, the minimal time step you can ever observe for your system, is much longer than this inverse frequency time, which is represented by the time at which your steady state distribution is reached. Suppose that the minimal time interval you can resolve is much longer than that. Intuitively, you see no acceleration whatsoever. To describe the dynamics at this very low resolution power in time, the acceleration term is the redundant. But there's a very simple way to see this. If you Fourier transform this, now let's do the following. Adding a force rather than the gravitational force, we use an arbitrary force, okay? And then we use a Gaussian noise, okay? That is delta correlated in time. Now, if I go to Fourier space, I perform the Fourier transform of this object, and I go to Fourier space, Fourier transform, this will give me minus m x tilde omega squared, right? The Fourier transform of the second derivative is fine. This will be whatever the Fourier transform of the force will be. The function of omega, I have no idea what it is, and I have no way to assume it's going to be small. Right? I will denote this Fourier transform of the force as a function of omega. I never use it. I just leave it there. And now here I will get like plus I omega m x tilde for the same reason. The Fourier transform now is one time derivative will give me a complex term. And then I will have the Fourier transform of a delta correlated noise, which is a constant. Right? Because the Fourier transform of a constant. So, the point that I want to make is that, now let me divide this by omega. Or I can divide out this by omega, for instance, squared. Or let's, what can we do? Yes, let me divide this by gamma, for instance. And write this omega squared as omega over gamma times omega. Now I have a gamma here and a gamma here. Now, as long as the Fourier modes that are important to understand the dynamics of the particle are much lower than gamma, you see, x of tilde of omega will have a Fourier spectrum. If the dynamics is slow, most of the Fourier modes will be in the low omega range and it will go out here, right? Now, I am now very schematically represent this as a cartoon, and probably this is just the modulus square of the Fourier components, right? The components will be positive, negative, not trying to make any particular sense. But the point is, there's going to be very little dynamics for very fast motion if the dynamics is slow, right? Now, if these modes are, say, omega, and gamma, and if gamma is here, then you see that for every Fourier mode where this is non-zero, I am suppressed by a power omega over gamma. You see, wherever x tilde is non-zero, so here, omega is much smaller than gamma. So this is much less than 1. Remember, physics starts whenever I can kill a dimensionless parameter that is much less than 1 or much larger than 1. Okay? So that means that if I want to represent the dynamics with the resolution power set by this low frequency mode of my system, so my system evolves slowly, have characteristic frequency modes that are inverse of the time scales of the evolution. If I'm interested in this slow dynamics, and this dynamics is much lower than 1 over gamma, I can completely neglect acceleration, because it's suppressed by a term omega over gamma. Is that clear? No?
Not in the Fourier space.
Yeah, but once you have something in the Fourier space, you can anti-transform back, and this translates into, as long as I'm interested in studying dynamics at low resolution power, I can neglect acceleration. It's just a mathematical way of seeing something that I've already stated intuitively. Okay? I first gave you the intuition that you reach a steady state velocity, and then you can forget about the transient. Now I'm making this slightly more elaborate and say, okay, you can see this mathematically by going to Fourier space and analyzing that there is a dimensionless quantity that is much less. Okay? Cute. Okay. But now things get extremely interesting. in principle, you got a simplification, right? Because you get rid of the second derivative. So let's write the corresponding equation. The corresponding equation is called overdamped Langevin equation. And the Langevin equation is simply obtained by taking the Langevin equation, setting to 0 the acceleration, and dividing everything by m gamma so that I have this x dot on the one hand. So in other words, I get x dot is equal to 1 over m gamma, well, let's say negative 1 over m gamma d by the x of u, plus the stochastic force divided by m gamma, right? Let me call it eta. Eta is nothing but psi divided by m gamma. So eta is the delta correlated zero average white noise where D is called the diffusion coefficient, and is equal to KD over m gamma. There are two m gamma because you see there are two m gamma, one dividing here and one dividing there. So the first kills this m gamma factor, and the second brings it downstairs. That's why we have KD over m gamma. It's called the diffusion coefficient. You with me? So in principle, this is easier, because now my equations of motion are only one dimensional, not two dimensional, sorry, first order differential equations, not second order differential equations. So in principle, it should be easier to integrate this guy than it would be to integrate the original Langevin equation. However, we immediately see we run into some problem. But before we see that, let's write a naive way of integrating this guy, right? Well, let me split this time derivative into x times t plus delta t, and x times t, divide by delta t, put delta t on the other side. Okay? What I'm going to write goes under the name of the Ito rule. Which looks like the most straightforward thing to be doing. So why does it deserve a name? But we shall see in a moment that there is much more to the picture than it meets the eye, as they say. It's far more complicated, but just wait for me. So the Ito rule is simply say, okay, let me label time now as a suffix. I could use t plus ti. Okay, but I like to label as a suffix for reasons. So x at time I plus 1 is equal to x at time I plus delta t the force at time I divided by m gamma. The force is, of course, negative the gradient of the potential, right? Plus delta t eta I. Now, if eta I is a random variable sample from a Gaussian, remember? Delta theta I is a rescale random variable sample from a Gaussian. Right? It's basically sample a Gaussian and extended by delta t. Right? If psi is a variable sample from a Gaussian, delta t times psi is just a psi sample from a Gaussian but with a broader distribution, or smaller depending on delta t. Right? Now, okay, fine. The probability of eta is e to the negative eta squared divided by some number that comes from here. Okay? The probability of delta t eta contains a delta t squared here. Right? So it's still a Gaussian. That's all I'm saying. So rather than call it eta and then multiply by delta t, we will refer this as the Wiener noise WE, which is still a Gaussian. The WE has zero average because the eta distribution has zero average. And what about WI, WJ, the delta correlation of the Wiener noise? Well, it's going to be taken from this equation, right? The delta correlation of the eta. Guys, it looks like I'm saying something complex, but I'm not. Are you with me? Okay. So how do we get that? Well, first of all, if we discretize time, we have to remember how to discretize a delta function. Well, of course, it connects to Kroneker's delta, right? But if you remember well, if I take delta of t minus t prime, ti tj, let me put a label now, ti tj, okay? And I discretize it. This is a Kronecker delta ij, but that's not it. I have to divide by delta t. Because remember, the volume of delta function must be set to 1. So if the size of the interval is delta t, the Kronecker delta must be divided by delta t. So the discretization of the delta function is, Dirac delta function is Kronecker's delta function, Kronecker's delta divided by delta t. So now, if I discretize these and I bring it there, I get 2d. Now, wi is delta t squared, and then 1 over delta t, delta ij, correct? I've taken this, multiplied by delta t to get the Wieners, and accounted for 1 delta t from the delta function. So this delta t here goes away with this. Okay? But this, unlike this expression, I cannot evaluate the delta function for t equal t prime because that's a distribution, it's not a function. But this is a representation of the delta function, which I can treat as a function, right? So I can see what happens when I equal to j. This implies that the variance of the Wiener noise is 2d delta t. So, in other words, the Wiener's noise is sampled from a Gaussian with variance with variance to the delta t, root of 2d delta t, sorry. The sigma is root of 2d delta t, because this is 2 sigma squared. Okay? So, operatively, how can I integrate the equations of motion? First of all, it's an equation, my system is now characterized by a first order differential for velocity. No longer a second order differential equation, which means my phase space has only coordinates, not momenta. Right? Because the dynamics of momenta is trivial. It's the equation of motion itself. Okay, there's no momentum if you have first order diffusion equation of motion. So my phase space is now reduced to configuration space. I cannot talk about velocities anymore. Okay? And how do I obtain the new configuration given the previous configuration? That's very simple. I start from a configuration 0. I evaluate the force multiplied by delta t divided by gamma, right? Which will give me a vector. This is 1 over m gamma delta t force calculated here. Okay? So that's F naught. That's x naught. This is the vector that this is the displacement due to the force, right? It's called the drift. Okay? Then I add a second number, a second vector, that is the Wiener noise, which I sample from a Gaussian. Now the Wiener noise, unlike the drift, couldn't care less about the underlying potential energy surface. It's sampled uniformly from a sphere with length determined by the diffusion constant, right? The larger is the diffusion constant. On average, the larger the variance will be, so the larger the distance displacement because of the noise will be. So let's say I get this error. I made a wrong choice because I go in the sign right into there. Let's say I get this error. Now, rule of how to sum, this will be my next position, x1. Displacement due to the drift, displacement due to the Wiener noise will give me next position. And now I can do the same. Compute the force in this position, add the noise, and I will get a new position. This kind of motion has a name, which I'm sure you know. What kind of motion is this? Brownian motion. So the overdamped Langevin equation generates Brownian motion. So trajectories look like, first of all, they're very edgy. You see, they have a lot of edges, because every time you have delta t, you lose memory of your previous direction. Right? Now, the fact that you lose memory can be rephrased with more scientific terms by saying that the configuration at time x plus 1 is determined stochastically, but only depends on configuration at times I. Right? It doesn't depend, for instance, on configuration at times I minus 1. Okay? Conversely, the original Langevin equation depended on two previous time steps. because the accelerations contains a second derivative, and to define the second derivative, we need two time steps, because it's the first derivative of velocity, and velocity itself is a displacement. So the Langevin dynamics is so dependent only on the last configuration in phase space, but not in configuration space. And the overdamped Langevin dynamics depends on the previous configuration in configuration space. This property of depending only on one configuration and not on the past is called Markovianity. So Langevin dynamics is Markovian. More specifically, the original underdamped or original Langevin dynamics is Markovian in phase space, while the overdamped Langevin dynamics is Markovian in configuration space. Now, in some sense now, we are getting closer and closer to Monte Carlo chains. In fact, Monte Carlo are called Markov state Monte Carlo, right? Markov chains. Why? Because in the Monte Carlo simulation, the next configuration will depend only on the previous configuration, right? Not on the previous to previous to previous to previous. Not directly. Of course, if you end up in a place, it's because you have the history. But where you go from a point depends only on that point. Okay? Even if it's stochastic. So Langevin dynamics is Markovian. And from this point on, we will only focus on overdamped Langevin dynamics. Although much of what we say can be said also for the original Langevin equation dynamics. With one fundamental difference that we're going to tackle right now. And after now, we're going to forget about the original Langevin dynamics. Although, when you run simulation, you have the option to select Nézet-Hoover or Langevin dynamics, for instance. When you select Langevin dynamics, what you're doing, you're integrating the original underdamped Langevin dynamics, which adds friction and noise to, for instance, leapfrog algorithm. Okay? Now, I want to go back on this picture, which shows Brownian motion and emphasizes the fact that at every step, you change direction in a completely random way. So in other words, Brownian motion is always non-differential. So in the limit in which I take the delta t discrepancy to 0, I get a time series where the derivative is never defined, right? Because the function is continuous but never differentiable in any point. It's the most irregular function you can think of, right? From the point of view of this algorithm, we couldn't care less because we have finite delta t we care about. However, every physicist has retained in its DNA a little bit of mathematician's attitude, no matter what culture and career it has. Something from your first year in calculus has remained in you. And this something must be struggling now, because I told you that the derivative of x is depending on the function eta, and that this eta is never differential, is never defined as a velocity. Right? So I get the derivative of a function that is not differentiable. What the hell is this? You see the problem? I just proved to you that x is never, I didn't prove it in the sense that a mathematician would call it a proof, but I think I convinced you that x, the trajectory of a Brownian motion, is never differentiable in any state. Yet, it comes from an equation where the derivative of x is written down, which assumes that x is differentiable. This is something that, of course, arises a mathematical paradox. And the paradox roots its origin very deeply into mathematics, giving rise to a very rich branch of mathematics. You see, we could go very deep up to a certain point. I could go and then into this rabbit hole, and then I would have to stop because I'm not a mathematician. But I want to make just a little step into the rabbit hole because it's very relevant. Clearly, if this makes sense in any way, it's not in the sense that Newton's had ever thought about it, or Leibniz, or later on, the formal definition of derivatives that we learned is based on. Because under that very definition, this is a non-differentiable function, so it makes no sense to define its time derivative. And not only that, is a non-differentiable function at any time.
This problem doesn't arise because we are assuming that eta as the delta.
Sure.
But then that came along just because we say that we can.
Very good. So you're giving us a physicist's way out of the problem. A physicist's way out of the problem is what I was about to say before mentioning the mathematician's rabbit hole. The physicist's way out of the problem is, hey, wait a minute, you're right, but we discussed that we are interested in dynamics at the resolution scale that is much longer than the thermalization scale. Now we learned the memory scale. And we learned in the first lecture of this course and in other lectures that I can never get any infinite resolution. So in the perspective of the effective theory that we discussed, delta t is always finite. And it not only is always finite, but it's sufficiently large for the physics to hold, the approximation to hold. So I don't care, that is good enough, right? Which is true. That's a physics-based argument for what we said. It's like when we discussed fluid dynamics. I want infinitesimal volumes, but not too infinitesimal, otherwise I fall into the vacuum between atoms. I want the volume to be small compared to the dynamics of the fluid, but large so that it contains many water molecules or fluid molecules, right? So my concept of infinitesimal is relative to something else. And the same happens to here. This delta t should be small compared to the dynamics of the system, but large compared to the underlying Kick's dynamics. So the fact that I'm not entitled to send delta t to 0 is good enough. Okay? But from the point of view of mathematics, this raises the problem of how do we define, since the mathematicians want to take the limit out. This gives rise of how do we give meaning to a calculus which has this property with some intrinsic noise over some scale. And you see, this gave rise to a branch of mathematics called stochastic calculus. And we are not interested in stochastic calculus. There is one point where we might need it, because the fundamental theorem of stochastic calculus is not the same as the fundamental theorem of calculus. So there are situations where you need to know just a little bit of stochastic calculus. But we are not going to run into that here. As far as we are concerned now, all we need to understand is why do we have this behavior? You see, because delta x, for normal calculus to work, delta x must be of order delta t, right? That's how you define a velocity. You have two objects of the same order, and then you take a ratio, and the limit is stable. But if you look at that, wi is of order root of delta t. You see, the variance is delta t, so that means that each, then you have to take, if you take the root squared, that of root of delta t. So delta x modulus is of order root of delta t. This roots into the concept of fractional derivative. But we don't need to know any of this. But this is the origin of why this is so different from this. Okay. Incidentally, this problem does not arise in the original Langevin equation. Because if you write the original Langevin equation, you have delta t squared. This is the acceleration discretized, and he has a delta t squared, right? Now, here is a bunch of terms which we know they are not problematic because we have solved them in conventional mechanics. It's the force term and the friction term. Right? They don't raise any problem, otherwise you would have noticed before, right? Let's go to the noise term here. Well, the noise term, right, is basically, remember, psi, and psi scales like root of delta t divided by delta t. Remember, because I still have this delta t, I have rescaled everything by delta t when I went to the Wiener noise from the eta. Remember? The Wiener noise that scales like root of delta t, right, was obtained sorry, no. Said something stupid. Sorry, said something stupid. This scales are root of delta. No, I was right. So, why? Because the Wiener noise appears after I multiply by delta t there, remember? xi plus 1 minus s1. So the Wiener noise is eta times delta t, which means that eta, which is proportional to psi, is 1 over delta t. Okay? The Wiener noise. And the Wiener noise scales like root of delta. Now, if I now integrate an original Langevin equation, I have to bring this delta t square on the other side. Right? Now, for Brownian motion, I had a term that was going like delta t, and a term that was going to root of delta t. So for small delta t, root of delta t dominates over this. Okay? Because delta t decays faster. However, if you do the same here, you discover that when you multiply by delta t, the leading term are these terms. Because they contain a 1 over delta t term here. The velocity contains a 1 over delta t term here. Right? So, and while this term contains a 1 over root delta t. So, in the original Langevin equation, the dynamics looks like this. Now, why am I doing all this? Because if I were to integrate my original Langevin equation, I wouldn't have to worry about any of this, because my dynamics of very small time scales is ballistic, is smooth. So it makes sense to use Big Frog. However, if I look at this a low resolution power, it means that I'm saying I have a configuration at some time, I have another at some time, I have another at some time, I have another, and now I look at this trajectory in this coarse-grained time representation, it becomes non-differential. Okay? Yes. I think I convinced you, maybe not, that if you were looking, first of all, we convinced that the problem with this, the lack of definition of delta t, is that the displacement was not proportional to delta t for small delta t, it was proportional to root of delta t. That's why I could not define a velocity. That's why I don't have a phase space, I only have a configuration space. Okay? Because velocities don't make sense. Okay? However, in the original algebra dynamics, if you do the same game and see what is the driving term in terms of small delta t, it is not the noise. It's a ballistic term, it's a deterministic term, which means that at small delta t, the trajectories are smooth, differential, so I can use leapfrog. However, I know that the Langevin, overdamped Langevin equation is the result of looking at the original Langevin equation at small resolution time, which corresponds to using large delta t if you want. And if I connect points reached by large delta t, they form a non-differentiable manifold. Okay? So, from this point on, we shall completely neglect Langevin dynamics in its original form, except by mentioning that you can use it as an integrator of your dynamics. And now we understand that it should be described in some kind of dynamics because it has some terms that effectively incorporate some of the interaction with the heat bath. Okay? But we haven't showed you that it's the right dynamics, that with fluctuation dissipation you fulfill the zeroth principle of thermodynamics. And we haven't shown you basically anything else. We will go back and revisit that, but for the sake of interest of time, from this point on, I will stick to the overdamped Langevin equation. Also because the overdamped Langevin equation is the basis of many AI-based algorithms, most notably diffusion processes, diffusion models. So when we will discuss AI application, which ultimately we will need to, given the name of the course, it's important to keep in mind some of the results that we're dealing with here. Okay? So, we know how to define a Langevin process. It generates Brownian motion with a drift term. We know how it relates to the original dynamics, even to the original Hamiltonian dynamics if you think about projecting out the solvent degrees of freedom, the heat bath degrees of freedom. We know how to integrate it. Well, that's problem solved, let's go home. Not really. First of all, we haven't made any advancements in the problem sampling configuration space, sampling dynamics, reducing the problems. Let's just have another integrator. Right? Now, to build some advances now, we need to tackle the problem of what probabilities look like in this dynamics. But now, we really make a deep step into dynamics and talk about two different types of probabilities. But clearly, being a stochastic process, I can only talk about probabilities at this point. Right? because there's nothing really deterministic anymore. Not only the initial condition is not deterministic, but even the dynamics itself is non-deterministic. So there's no meaningful single trajectories I can do. But now I can define two probabilities. The probability of finding a system at point x of configuration at time t, which I will probably refer to as configurational probability. And another probability. Let me write it this way. That is the path probability, or trajectory probability. Let me tell you what do I mean. Well, this is what you think it is. It's the probability that you make a measurement that finds the position at time t and you find it in x. It's whatever enters the equivalence of the Liouville's equation for this system. Okay? This is instead is the probability of observing a given trajectory and collections of frames, time-ordered collections of frames. Now, I can assign a probability now to a frame, to a trajectory, unlike I could in principle do it also for Hamiltonian dynamics, but it would be an extremely boring distribution. It would be a delta function around the only solution you get of the Liouville's equation, of the Hamilton's equation given an initial condition, right? You have an initial condition in phase space, you have only one trajectory, your path probability in phase space would be the only trajectory you can get. Because remember, in Hamilton's dynamics, all the stochastic nature of the dynamics is inherited from the initial conditions. While in Langevin dynamics, this is no longer the case. And this is part of the reason why this is so much more handy to do things. There is an intrinsic stochasticity, which means that anytime I repeat the process, I get a different trajectory, in spite of the fact that I start from the same initial condition. We discussed that at the beginning. So I can, in principle, assign a probability to each of these paths. And make no mistakes, these paths, probability, is a very, very relevant object. Think about this. We built a company on that. For some reason, as we shall see probably, we were able over the years to develop an algorithm that could do one thing and one thing only. I'll show you movies at some point. Predict the folding pathways of a protein, even including the ribosome, so assuming that you generate the amino acid one at a time, knowing the native state. So in some sense, the complementary problem in protein folding to what AlphaFold has already solved, which is tell me the native state given the sequence, right? So we developed an algorithm that, for some reason that I will argue, is able to predict protein folding pathways, even with or without the ribosome, doesn't matter. And these algorithms work efficiently because we are able to master this probability of the path and redirect the algorithms towards generating paths with large probability, okay? So, in some sense, there are many algorithms, including others developers algorithms, which I will also refer to later on in this course, such as transitions and that are speeding up the generation of this path relative to just integrating forward equations of motion by exploiting the fact that you can calculate this probability. Now, to give you a hint of how relevant it is, for what we did, we figured out that we were able to do that very accurately, and I'm citing this as an example. There are certainly 100 different examples of this. I'm not saying that we were the only one to have anything relevant here. I'm just giving this example because it's the one that I happen to be involved with, so I know better than the others, okay? So in our case, we were able to predict, to generate protein folding pathways with high accuracy, knowing the native state. And what we figure out is that this pathway has a certain probability, and this probability is such that the protein very often, biologically relevant protein, visit certain folding intermediates, which are partially folded structure, which we could predict by numerical simulations. Now, these folded intermediates have binding pockets that are not exposed to the solvent where the protein finishes the folding. For instance, there's a pocket that gets covered by a helix. But we could predict that you visit that pocket because we knew the probability. Now what we did, we'd use this information to design small molecules that bind to those pockets and make it impossible for the folding to complete. If you have a protein that doesn't manage to fold, it remains unfolded. The cell quality control machinery recognizes it and immediately sends out quality control machinery's workers, kinases or whatnot, to target that for degradation. So the protein gets destroyed. Now, if that protein is a pathological protein, for instance, a protein that is overexpressed during cell replication in cancer, you have all of a sudden a way to suppress the expression of that protein because you stabilize its folding mechanism, make it impossible for the protein to fold, and immediately the cell gets rid of it. So this seemingly impossible technology works. We have proven it in a number of papers, and now we founded a company that is closely approaching clinical trials. Probably preclinical phase will be starting this year. I don't know. I don't want to make promises. It's not my business, but it's been through intense drug discovery programs and finding drugs for systems for which the conventional pockets don't work. Maybe the protein is undruggable. Okay, think about neurodegenerative diseases where the pathology originates from the protein aggregating in a misfolded state. Conventional drug discovery wouldn't work for that. Why? Because conventional drug discovery is based on finding molecules that bind, rational drug discovery, to the active side of the protein, making it difficult for the protein to be active. But Alzheimer's, or even better, prion diseases originate not because this prion protein is active, but because it misfolds. So if you altogether remove the protein or reduce its expression, you reduce the amount of misfolded protein in solutions. So in principle, this is a scheme that opens the way to new pharmacological treatments that are alternative to existing ones for which conventional methods don't apply. So I'm taking this, first of all, because it's perhaps the most relevant contribution I've done together with my colleague Emiliano Biasini, with whom we co-invented this. I should say we are equal inventors. I'm not claiming 100% credit for this. 50% is the fair amount. First of all, because, okay, I happen to be happy because this is perhaps whatever it means, the most relevant thing that I've done so far. But most importantly, because it shows you how molecular simulations, coupled with understanding of the physics behind it, so that you can control the physics, you can break the code, so to say, can push applied physics and applied biology, applied pharmacology forward. So that's why we didn't just stick to the program today. Okay, we now know what the Newton's equations are. You have a code to simulate proteins, go ahead and simulate. I wanted to convince you that knowing stuff, breaking the box and looking into the black box and see how it works can inspire even things as concrete and practical as drug discovery methods. Okay? So what we're going to do next time is to find the equations for this. Well, we'll see whether we'll find it. I have, I think, 4 different independent derivations of it in notes. I'm not sure I will need to give you one. I will probably just state the equation. After all, you never really wanted to know the proof of the Schrödinger equation if there was any. Right? And then discuss the path probability. And the result will be that this is obtained from this through an object called the path integral. So there will be a connection between the two. Okay, I think I can stop here.